This part of the lecture is going to go over sections 21.7, 8, and 9. So when we're looking at here for mutual inductance and self-inductance, when we have a changing magnetic flux and it's created by a changing current in one circuit, and that's going to link, let's try this again. When changing magnetic flux created by a changing current in one circuit links a second circuit, an EMF with magnitude E sub 2 is induced in that second circuit. So in other words, you got two circuits that are close to each other. You got a changing magnetic flux in one. It's going to end up inducing another one in the other. The changing current in the second circuit induces an EMF with magnitude E sub 1 in the first circuit. So how do we figure out what these two EMFs are? We've got E sub 2 is equal to M, which is going to be a constant called the mutual inductance. A changing current, I, in any circuit induces an EMF in that same circuit called a self-induced EMF, and that's given by this, where L is a constant called the inductance or self-inductance. All right, so you have here the EMF in two that comes from the changing current in the first circuit. You have the EMF that is induced in circuit 1 by the changing current in the second circuit. And then you have an EMF that's induced in the circuit itself by its changing current. And there's a lot going on there. I get that. So self-inductance, if the current I in the coil is changing, the changing flux through the coil induces an EMF in the coil. And we'll get to a little bit of that here in a second. So let's actually go to that. And then we'll talk about transformers. Okay. So the question here is, how does a 12-volt car battery produce the thousands of volts needed to produce sparks across the gaps of spark plugs in the engine? In other words, it doesn't seem like you're starting with much. So electrical transmission lines often operate at 100,000 volts or more. Applied directly to your household wiring, this voltage would incinerate everything in sight. So how can it be reduced to the relatively tame 120 or 240 volts required by your electrical appliances? So in other words, you're starting out with low voltages. How do you get to the high voltages? What's the mechanism here? So the solutions to both of these problems, basically a step up or a step down. And to many others concerned with varying currents in circuits, involve the induction effects we've studied in this chapter. So a changing current in a coil induces an EMF in an adjacent coil. So the coupling between the coils is described by their mutual inductance. So this interaction is the operating principle of a transformer, and we'll get to that in just a minute. So what does all of this mean to you? So one application is the modern electric toothbrush, and that uses an inductive scheme to recharge the batteries. So the base of the toothbrush sits on the base that it sits on produces an oscillating magnetic field that in turns induces an oscillating EMF in a coil in the toothbrush handle. This EMF is then used to recharge the battery. The advantage of using the inductive charging is that the user does not have to plug anything into the brush handle, which circumvents the problems with moisture, since you use water on these toothbrushes, short-circuiting the unit. So you've got two coils of wires here in this particular cross-section. The current I in coil 1 sets up a magnetic field, which you can see it there in the blue wires, or the blue lines. And some of the fields pass through coil 2. And we denote the magnetic flux through each turn of coil 2 caused by the current I sub 1 in coil 1 as the magnetic flux of B2. So we're using the lowercase letter I with a subscript for time varying currents. So in mutual inductance, a portion of the magnetic flux sets up by a current in coil 1 links with coil 2. So the magnetic field is proportional to that current in I1. So the flux in B2 is also proportional to I1. When I1 changes, B2 changes, inducing an EMF 2 in coil 2 with this magnitude. So in other words, the EMF, as you might guess, is proportional to the change in the magnetic flux in B2. Question is, what's this N out here? That is going to be the number of turns in coil 2. So we can represent the proportionality of the flux in B2 and I in terms of this form, but instead it is more convenient to include the number of turns, introducing a proportionality constant M21. We're going to write it like this. So from this relationship, the change here is going to be the same as a change in the current since this constant doesn't change. And we can turn around and we can rewrite this as M21 times the change in the current. We can repeat this for the opposite case in the first coil and how that relates to the change in the current or the magnetic flux in that particular coil. And this is what we come up with. So we might expect the corresponding constant would be different from this because in general, the two coils are not identical and the flux through them is not the same. But as it turns out, it's always equal, even when the two coils are not symmetric. So we call this the mutual inductance. In other words, there ain't no point in distinguishing between 2 to 1 and 1 to 2. Mutual inductance is going to end up being the same in both cases. So Tesla coils, which you may have seen up to this point, and there are some pretty good videos out there regarding what you can see with these Tesla coils. So this is a type of high voltage generator. It was invented by Nikola Tesla. You may have seen one in a science museum. And again, there are some videos out there. In one form of a Tesla coil, a long solenoid with length L and cross-sectional area A. It's closely wound with N turns into 1 turns of wire. Then you got a second coil, turns surrounds it at its center. So you can find the mutual inductance of those particular coils. So you can see here that the current in the solenoid sets up a magnetic field at its center. According to equation 20.14, the magnitude B of the magnetic field at the center is given by this. You can solve for N, or the number of turns, as you find out here. You can take this and rearrange it so that it looks like this. The flux through each turn at the center of coil 1. The flux there is equal to B times A. All of this flux also passes through coil 2. So this is equal to this, which is equal to this. So solving for this, the mutual inductance ends up being this, or this, or this, or this, which is a number of turns. So once you're actually given values for a lot of these particular variables, and you can go through and you can figure out what the mutual inductance is, which is going to be given in Henry's. So you have other problems there that you can work through. All right, so let's consider two coils, A and B. that have mutual inductance M. So let's say a physics student attaches a power supply to coil A and increases the current to 10 amps over a period of 5 seconds while measuring the EMF in B. Experiment is repeated by increasing the current in B in exactly the same way while measuring the induced EMF in A. Which of the following statements is going to be true? The mutual inductance is given, so we do not have to concern ourselves with the details of coil geometry and relative orientation. Time rate of change of the current was the same in each of the measurements, therefore the induced EMF will be the same for each coil. So now let's go on to 21.8. Solve inductance. So for mutual inductance, we assume that one circuit added as a source of magnetic field and that the EMF under consideration was induced in a separate independent circuit with some of the magnetic flux created by the first circuit passing through the second. However, when a current is present in any circuit, this current sets up a magnetic field that links with the same circuit and changes when the current changes. So any circuit that carries a varying current has an induced EMF in it resulting from the variation within its own magnetic field. This is called self-induced EMF. So as an example, consider a coil with N turns of wire carrying a current I. As a result of this current, the magnetic flux passes through each turn. In analogy to equation 21.10, we define the inductance of the circuit as the self-inductance, which looks a lot like what we had seen before with the mutual inductance. So if the current in the coil is changing, the changing flux through the coil induces an EMF in the coil. So if the flux and I change with time, we end up with this particular equation. So this changing with time is essentially what this one comes from. We know from Faraday's law that this is equal to E. So then we can replace this with E and we come up with this, the definition of self-inductance. So a circuit element that is specifically designed to have a particular inductance is called an inductor. Like resistors and capacitors, inductors are indispensable in modern electronics. In later sections, we'll explore how simple circuits containing an inductor behave. The usual circuit symbol for an inductor is basically this. So we can find the direction of the self-induced EMF from Lenz's law. The cause of the induced EMF is the changing current in the conductor, and an EMF always acts to oppose that particular change. In this figure, the current is constant, so the change is always 0, and then the voltage is going to be 0. If we look at problem B, where we have increasing current, then we have EMF that is working to oppose that particular change. Obviously, the voltage between A and B is going to be considered greater than 0. If the current is increasing, okay, sorry. Okay, so we got that constant. We've got this. Okay, that is B. Sorry. So for part C here, if the current is decreasing, then by Lenz's law, the EMF points in the same direction as the current in order to be able to continue to boost that particular voltage. Doesn't like to see the change. Again, this is nature that is wanting to keep things the same. So another example here, an air coil toroid solenoid, toroidal solenoid with cross-sectional area A and mean radius R is closely wound with N turns of wire to determine the self-inductance. In calculating the flux, assume that B is uniform across a cross-section. Ignore the variation of B with distance from the toroidal axis. So if we're looking for the self-inductance here, we're going to use this particular equation. To find the magnetic flux, we first find the field magnitude B. We know that from a toroid that B is equal to this particular equation. If we assume that the field has a magnitude over the entire cross-sectional area A, in other words, it's not cutting short out of that particular area, then the flux is going to be the product of B times A, which is basically all of this multiplied by A. All the flux links with each turn, and therefore the self-inductance is going to be the product of this times the rest of this, and we end up with this. If we have certain numbers that we can plug in here, we can figure out what that self-inductance is. Mutual inductance and self-inductance are both going to be measured in henries. So, application. So we're all familiar with the parking lot gate that opens automatically as you pull up to the exit. Presence of your car is detected by a coil that is built into the roadbed at a position that is just inside the gate. So when you approach the gate, the iron in the car dramatically changes the inductance of the coil. Current, a circuit registers this change and opens the gate. Usually the gate will not open for a bicycle simply because a bicycle does not produce a big enough inductance change to trigger the detection circuit. So that's something you can take with you. As you have seen, the inductance of a circuit depends on its size, shape, and number of turns. For N turns close together, the inductance is always proportional to N squared. The inductance also depends on the magnetic properties of the material close to the circuit. We assume that the conductor was surrounded by a vacuum. If the flux is concentrated in a region containing a magnetic material with relative permeability K, then in the expression for B, we must replace mu naught, the permeability of the vacuum, by K sub M times mu naught, as discussed in section 20.11. If it's ferromagnetic, the difference is of crucial importance. An inductor wound in a soft iron core that has, I think I call that K sub M, but I don't think that's right. That has K equal to 5,000, has an inductance approximately 5,000 times greater as the same coil with an air core. Iron core and ferrite cores, inductors are widely used in a variety of electric power and electric applications. So let's say a physics student attaches a power supply to a coil with an inductance L and drives a constant current of 10 amps. He then measures the EMF across the coil, and then he repeats the experiment with a current of 5 amps. So which one of the following statements is true regarding the measured EMFs? Well, the inductive EMF can arise only if there's a change in the magnetic field. Because the coil produces its own magnetic flux, the flux can change only if the current is changing. In each case, the student is driving a constant current, so the EMF in both measurements is going to be 0. So in other words, they are both 0. So now let's go to transformers and let's kind of talk about that. So a transformer is used to transform the voltage and currents in an AC circuit. An alternating current in either winding results in an alternating flux in the other winding, thus inducing an EMF. In an ideal transformer with no energy losses, if the primary winding has N sub 1 turns and the secondary winding has N sub 2 turns, then the voltages are related by this. So you've got an AC source here, you've got primary winding, you've got an iron core, you've got secondary windings here, N sub 1 turns here, N sub 2 turns here, and you've got a certain voltage here and then a voltage here. So for an ideal transformer, the ratio of V2 to V1 is the same as N2 to N1. So if you want to boost the voltage here, guess what you got to do? You got to add a ratio of the number of turns that you've got here over here in order to be able to boost that voltage. So one of the great advantages of AC current, in other words, usually varying sinusoidally with time, over direct current, which doesn't vary with time for electric power distribution, is that it's much easier to step voltage levels up and down with AC. For long distance power generation or power transmission, using as high a voltage and as small a current as possible, it also reduces the power loss due to heat. As a result, smaller wires can be used for a given power level, reducing material costs. Present-day transmission lines routinely operate at voltages in the range of 50 kilovolts to 250 kilovolts. However, safety considerations and insulation requirements dictate relatively low voltages in generating equipment and in household and industrial power distribution. Standard voltages for household wiring is 120 volts in the US and Canada and 240 volts in most of Western Europe. The necessary voltage conversion is accomplished by the use of transformers. So in the discussion that follows, the symbols for voltage and current usually represent amplitudes. In other words, maximum amplitudes of quantities that vary sinusoidally with time. In fact, alternating voltages and currents are usually described in terms of the root mean square values. So for sinusoidally varying quantities, there are less than the maximum values by a factor of about 1 over the square root of 2. So for example, the standard 120 volt household voltage has a maximum or a peak value of 170 volts. And we'll talk about that in chapter 22. A transformer consists of two coils, usually called windings, electrically insulated from each other, but wound on the same core. We discussed the mutual inductance of such a system. The winding to which power is supplied is called the primary. The winding from which power is delivered is called the secondary. Transformers used in power distributions have soft iron cores, and the symbol for an iron core transformer is this. So an alternating current in either winding sets up an alternating flux in the core, and according to Faraday's law, this induces an EMF in each winding. Energy is transferred from the primary winding to the secondary via the core flux and is associated and its associated induced EMFs. So if you take a look at these cans, these are step-down transformers that bring the voltage down from 2400 volts put out by the local substations to the 240 volts commonly distributed to houses. Substations have transformers that bring down the voltage from much higher values, typically 200,000 volts or more of long distance power lines. Power stations use step-up transformers to create these high voltages. So an idealized transformer in figure 21.28 is shown. We'll assume that all of the flux is contained or confined to the iron core. So at any instant, the magnetic flux is the same in the primary and secondary coils. We also ignore the resistance of the windings. The primary winding has N1 turns and the second has N2. When the magnetic flux changes because of changing currents in the two coils, the resisting induced EMFs are given by these, which you probably remember up to this point. The induced EMF per turn is the same in both voltages, so we adjust the ratio of the terminal voltages by adjusting the ratio of the turns. If the windings have zero resistance, the EMF, the induced EMFs are equal to the corresponding terminal voltages, and we find the following. Basically this. So by choosing the appropriate number turns ratio, we may obtain any desired secondary voltage from a given primary voltage. So if we end up with more voltage than what we started with, we've got a step up. If we have less than what we started with, we have a step down. So if the second circuit is completed by resistance R, then I sub 2 is equal to V sub 2 divided by R. For energy considerations, the power delivered to the primary equals that taken out of the secondary. So V1 I1 is equal to V2 I2. And with that particular relationship, we can figure out how the turns of the coils are related. So this equation shows that while the secondary circuit is completed through a resistance R, the result is the same as if the source had been connected directly to the resistance equal to R divided by the square of the turns ratio. It transforms not only voltages and currents, but resistance as well. So the transient electrical signals from excitable animal tissues generate tiny magnetic fields generated generally below the detection limit of the usual devices for measuring magnetic fields. However, something called the squid uses a detector coil that is superconducting. In other words, it has zero electrical resistance. Careful shielding from stray magnetic fields and other tricks, the device can measure magnetic fields smaller than 1 × 10⁻⁻15 teslas. These have been used to detect the fields generated by a single nerve impulse, the contraction of abdominal smooth muscle, the fetal heartbeat, electrical storm in the brain that accompanies epilepsy. Brain imaging with a squid is faster than MRI because the squid directly detects electrical activity by way of the tiny magnetic fields, where this MRI detects increased blood flow to active areas of the brain. Now, real transformers are going to have some sort of energy loss. The windings are going to have resistance, although superconducting transformers may negate that. There's also energy loss through eddy currents, which is kind of what you're seeing here in the core. The alternating current in the primary winding sets up an alternating flux within the core and a current in the secondary winding. But that iron core is also a conductor, and any section such as A can be pictured as having several conducting circuits, one within the other. The flux of these circuits is continually changing, so eddy currents circulate in the entire volume of the core, wasting energy through heat. So that gives you a basic idea of transformers.